Hello everyone, my name is Suki Lee, a PhD student at the University of North Carolina at Chapel Hill. I'm going to present our RTAS 2020 paper titled SubFlow, a dynamic induced subgraph strategy toward real-time DNN inference and training. Let's start with the motivation of SubFlow. Nowadays, many real-time applications are increasingly using deep neural networks for real-time intelligent tasks. For example, autonomous vehicles perform object detection tasks by using convolutional neural networks in a limited amount of time to ensure safety. And machine translation systems translate text from one language to another with deep learning to provide a seamless and natural conversation. Many of these applications are time-sensitive, which requires the completion of a job with a timing guarantee. However, executing DNNs in a real-time manner is challenging. The first challenge of real-time DNN stems from long and unpredictable execution time, resulting from a significant amount of computation required by modern DNNs. For example, here is a VisiNet having 16 layers with 138 million parameters. When we classify 16 ImageNet dataset samples with VisiNet by using a multi-core CPU, it takes 3100 milliseconds, which requires a long execution time. When we use a high-end GPU for the same classification, its completion time ranges from 59 milliseconds to 143 milliseconds, which results in very unpredictable timing behavior. The second challenge of real-time DNN comes from the fact that the timing constraints of many real-time systems dynamically change at runtime. This is more problematic to most DNNs since they are not flexible to adapt to dynamic timing constraints. Let's see autonomous vehicles that need to detect objects such as humans or cars on the road as an example. The real-time requirement of obstacle detection tasks in these systems becomes tighter when the vehicle is moving at a relatively higher speed, requiring the DNN to complete its processing faster. In contrast, when the vehicle is moving at a slower speed, the timing requirements are relaxed, allowing more time for the DNN to complete execution. These two video clips show city driving situation and highway driving situation where their latency requirements for object detection are significantly different. Here, for example, 10 milliseconds versus 100 milliseconds. Many existing works are trying to solve the real-time DNN problem. One of them is to leverage the power of high-performance hardware such as multi-core CPUs or GPUs. Although they can efficiently process the massive workload of DNN in parallel, the complexity and proprietary architecture of these platforms make effective scheduling of deadline-aware DNN tasks still challenging, as shown in many previous studies. We introduced SubFlow that enables dynamic real-time DNN execution at runtime, which completes the execution of DNN given dynamic timing constraints using induced subgraph that are formed from a subset of the vertices of the original DNN and all of the edges connecting parts of vertices in that subset. Here is an example of SubFlow. We have a DNN whose execution time is 50 milliseconds. But when the allowed execution time is changed to 25 milliseconds at runtime, the DNN cannot be completed in the time since the new timing constraint is tighter than 50 milliseconds. However, SubFlow enables the system to complete the DNN task within 25 milliseconds by constructing an induced subgraph of the original DNN architecture. For each execution of the DNN, SubFlow allows a flexible trade-off between execution speed and inference accuracy based on the system or application requirement, while providing comparable inference accuracy at the same time. SubFlow operation takes 3 steps. The first step is to rank the neurons layer by layer based on the importance to the final performance of the DNN. When given a dynamic timing constraint for feed-forward or backpropagation, the second step of SubFlow is to construct a dynamic subnetwork whose total amount of computation can be completed within the given time budget based on the neuron rankings obtained at the first step. The last step is to perform the time-bound execution of the dynamically constructed subnetwork at the second step. The first step is performed at compile time, and the second step and third steps are performed at runtime. Let's take a look at each step in more detail. The first step of SubFlow ranks all the neurons in the DNN based on the sensitivity to the final output of the DNN, which measures the error increase when the neuron is removed from the DNN. We use the second-order derivative when measuring the importance in order to minimize the performance loss of subnetworks. This neuron ranking step is performed only once at compile time. The second step of SubFlow is the dynamic construction of a subnetwork that can be completed within the given time budget, B, by determining the dynamic size of subnetwork and by selecting layer-wise neurons to be activated. Here we have a DNN with 3 layers where each size is denoted as 1.0. When the execution time budget is shortened to 25 milliseconds, SubFlow first determines the size of subnetwork, which is 0.5 in this example, which means the size of subnetwork is half of the original full-size network. And then, based on the neuron ranking obtained from the first step, the best subset of neurons at each layer is selected to construct an induced subgraph. The last step is to complete the execution of the dynamically constructed subnetwork at the second step within the time budget. The execution step is required as a separate process since the time-bound execution of subnetwork entails technical and practical issues that need to be handled accordingly. Here we have the subnetwork of size 0.5 constructed at the second step. The basic idea of time-bound execution is to skip the computation of deactivated neurons. The detailed execution process depends on the network architecture. SubFlow supports convolutional layers and fully connected layers, which are the 2 main building blocks of modern DNNs. The first case of time-bound execution is convolutional layers. Here we have a convolution operation with 3x3 input and 2x2 convolution filter, which results in 2x2 output. The blue element denotes it is activated, while the gray element denotes it is not activated. To perform the convolutional operation, the input is first unfolded into a vector as a single column, and then the output is also unfolded into a vector as a single row. The convolution operation consists of multiplication that is shown in horizontal direction and addition that is shown in the vertical direction. To complete the first element of the output, the convolution filter is unfolded into a vector. However, since the first element of the output is deactivated, the entire convolution operation, including both multiplication and addition, is skipped. To compute the second element of the output, the convolution filter is unfolded again into a vector. Since the 2 elements of the inputs are deactivated, the corresponding multiplications are skipped, and only 2 elements of convolution filters are multiplied with input and added to the obtained output. When computing the third element of the output, only two elements of convolution filters are multiplied and added by skipping the computation of the other two elements due to the deactivated elements corresponding to them. Lastly, the computation for the fourth element of the output is entirely skipped since the fourth element of the output is deactivated. By performing convolution operation only with the activated neurons and skipping the computation of the activated neurons, time-bound execution becomes enabled by improving the speed of multiplication and addition 4 times and 6 times respectively. The second case of time-bound execution is fully connected layers which require to perform matrix multiplication. Here we have matrix multiplication operation with 1/3 input and 3/3 weight parameter, which result in 1/3 output. Since the first element of the output is deactivated, the first column of the weight parameter matrix becomes unnecessary to compute. Also, since the second element of the input is deactivated, the second row of the weight parameter matrix becomes unnecessary to compute. As a result, the matrix multiplication between 1/3 input and 3/3 weight parameter matrix turns into a matrix multiplication between 1/2 input and 2/2 weight parameter matrix. It enables the time-bound execution of a fully connected layer by achieving 2.25 times and 3 times fast execution for multiplication and addition respectively. To evaluate SubFlow, we implemented an autonomous mobile robot that detects obstacles in the depth map of the camera image. First, the camera takes an RGB image, and then it is fed into the convolutional neural network that generates a depth map of the RGB image in which obstacles are detected. The information of the obstacles, such as the location and size, are passed into the navigation system that controls the motors and wheels of the robot to avoid the obstacle accordingly. Since the obstacle detection and avoidance is critical to the safety of the mobile robot, the timing constraint of the depth map generation dynamically changes according to the velocity of the mobile robot at runtime. To put it simply, the faster it runs, the quicker the depth map CNN needs to be completed. For example, when the robot is running at 2 cm per second, the depth map generation CNN with SubFlow translates the RGB image into the depth map in 200 milliseconds. However, when the robot increases the speed and runs at 4 cm per second, which is twice faster than before, SubFlow generates a depth map in 100 milliseconds to enable a faster reaction to the obstacle. SubFlow translates an RGB image into depth map at a dynamic rate with a comparable error. When the robot is running at 2 cm per second, it translates the RGB image into depth maps per second with an error of 0.04365. But when the robot is running at 4 cm per second, the translation rate increases twice with an error of 0.05482. These two video clips compare the translation rate for the slow running case and the fast running case, where the fast running case translates RGB images twice faster than the slow running case. In conclusion, we introduced SubFlow that enables dynamic real-time execution of a DNN based on the Induced-Subgraph strategy. We propose a subnetwork construction algorithm and the time-bound execution of convolutional and fully connected networks. We implement an autonomous robot and demonstrate that its object detection task is completed within the time budget that dynamically changes based on the running speed of the robot. Thank you.